Okay, good morning. So yeah, it's going to be, I guess, something a bit different from what you've heard. I'm going to be talking about paleoclimate. I'm not going to be talking about extreme events such as you've heard, I guess, this week. But we'll be looking at pretty large and abrupt changes that occurred in the past. So today I'm going to focus on what we call millennial scale variability of the last glacial period here. But in order to introduce that to you, we'll first just go over a brief overview of glacial interglacial cycles, because maybe some of you just don't know what it is. And we'll finish up on to some perspective or understanding why this variability is important for today and for the future. What is the relevance of those changes? So first, again, since I'm not sure what your expertise is, I start with something very simple. It's just how can we estimate past climate change? I guess the first question, how do we know what happened in the past? And there are actually two methods to estimate past change in climate. One is what we call the paleoproxy record, and the other, of course, are just numerical models, the same models that we use for present day and future climate. So there are a range of what you call paleoproxy records. They can be ice core records, like here, coming from Greenland or Antarctica, and we'll just talk about this in more detail in a moment, or marine sediment cores, so you just go not right in the middle of the ocean because you need to have some sediment, so you go on the continental shelves and you try to get a record of sediment with the deeper time, the oldest sediment being at the bottom and the most recent at the top. And from there you can try to pick the little creatures, so most of the time those are foraminifera, little creature made of a calcite shell, and you can analyze those shells and try to understand what happened in the past based on the isotopic composition of those calcite shells or others. You can also look at other records such as paleothems, corals, or even lacustrine sediment cores. So there are a range of methods on the paleoproxy side to try to estimate past changes, and I will present some of those records today. So the other method is, of course, numerical experiments. So you can have a coupled model, a model representing the evolution of the ocean, the atmosphere, the land. And those coupled models can be forced by changes in what we call orbital parameters, so the insulations that reach the Earth, changes the ice sheet, because there were large changes in ice sheet over glacial interglacial cycles, and change in greenhouse gas. And those models can run, and the output can give you an understanding of what happened in the past. So you can do a range of experiments, from very simple experiment to complex transient experiment, to try to understand what happened in a dynamical sense. And it gets very interesting when you can compare both methods, use the results of numerical experiment and compare that with paleoproxy records to try to understand where there is agreement, why there is agreement, or on the same, why there is a disagreement in between what the models say and what the proxy say. So yeah, I just wanted to give you a bit more detail on ice core records, because I'll be presenting quite a few of them, and they're a fantastic archive. So here you have Greenland and Antarctica with some of the main coring station, if you wish. So cores that have been taken at those different locations, so N-grip, North grip in Greenland, for example, or GISP record, and in Antarctica, maybe Epica Domsey over there. And those records are fantastic because we can estimate temperature change, either in Greenland or Antarctica, by looking at the isotopic composition of the ice, so the oxygen isotopic composition, or the deuterium, which is a ratio of the heavy hydrogen over the more normal hydrogen, if you wish. But you can also have an indication of changes in atmospheric gases, so greenhouse gas, carbon dioxide, methane, etc. And so this is possible because this is a very simplified view of an ice core with the oldest ice here, and this is the surface, which can just be snow. And as there is a transformation in between snow and ice, some of the gas bubbles, so gas bubbles of gas will be trapped here, start to be trapped in the matrix, and then be preserved here in what we call the deep ice or the firn ice. And you can then analyze those gas bubbles, and that will give you a composition of the greenhouse gas a long time ago. So I think now we're almost going back to 1 million, so the oldest ice is about 800,000 years old, so you can have the evolution of those gases through time, so mostly from Antarctica. This is what we see here. So this is just the last 450,000 years from a Picadom sea ice core in Antarctica. And we can see here the evolution of the atmospheric CO2 content. So with period of high atmospheric CO2, which we call interglacial time, so warm time, and we are here. Well, not really, because we are here. But we would be in a natural world, or just 200 years, we would be here just at 280 ppm in a warm climate. And here you can also have an estimate of temperature in Antarctica during this same time period. And again, you can see the fluctuation in temperature in between a warm interglacial state going slowly down into a glacial state. And the fantastic things, the things that strikes us directly when you look at that is the clear correlation in between the temperature change in Antarctica and atmospheric CO2, so globally average. So on a glacial, so if we look at the glacial interglacial time scale, so we have large changes in temperature at the pole, we have large changes in atmospheric CO2 in between 180 and 280, and we also have large changes in ice sheet. So this is the result of a model for the last glacial maximum here about 20,000 years ago, showing the expansion of the ice sheet over most of North America, so covering most of the Canada and down to the United States. It's what we call the Laurentide ice sheet, and also an ice sheet over most of Eurasia. So those glacial, interglacial cycles, we're starting to have a fairly good understanding of them, and we know that there are several things that lead to those cycles. So one of the main external forcing are changes in insolation. So as the Earth's orbit around the Sun varies, it varies in time. So this is what we call Milankovitch cycle. So the eccentricity, precession, and obliquity varies, which changes the insolation that, or the magnitude of the insolation on Earth has a significant impact in driving those cycles. However, they are not sufficient. If you just have changes in insolation, you cannot explain those changes. And there are two, what we call internal forcing, or positive feedbacks, which are change in atmospheric CO2 and changes in northern hemispheric ice sheet. So as atmospheric CO2 changes, the radiative balance changes, and it can lead to either a significant cooling or warming, depending which state you are on. And also, the northern hemispheric ice sheet have a strong impact through their albedo effect or topography. Okay, but this is just to introduce you to what we call here the last glacial period, which is what I'm going to focus on today. And when we zoom into that period, so here we're going to zoom into here, but not looking at Antarctica, we're going to look at Greenland this time. And we have these pictures, so this is just Delta 18O record of the ice in Greenland over the last 60,000 years. So here we are during the glacial period. We have the last glacial maximum here about 20,000 years ago, the deglaciation, and going into present day here. And there's something that is really striking in that picture. It is this really high variability that we have during the last glacial period. So you can see here we have a full glacial interglacial cycle with a magnitude of change in of temperature in Greenland of about 14, 16 degrees, maybe. And here we have those changes with an amplitude of about 8 degrees in Greenland. And they occur, again, on a millennial time scale, but they're very rapid. So if we zoom into that again, so simply what happened here is that they just stacked up all those events into the cooling event and the warming event and tried to look into them in detail to see the rapidity of the change. And so here we have a warming event, so Greenland temperature is in blue, and here we have a cooling event, and what you can see is that temperature in Greenland can increase by 8 degrees Celsius in less than 50 years. And it can also decrease significantly, maybe, again, by 50 years to about here, like 3/4 of it, and then maybe it's a bit slower towards the end. But those are very large changes, they're very rapid, so it's less than a century. And on top of this, there's also the methane concentration, so in the air, which can be measured in the same ice core in Greenland. And this gives you an indication of northern hemisphere terrestrial biosphere changes. So it's more an integration of changes maybe in a tropical wetland, for example, or a high latitude permafrost and so on. And here you can see significant changes as well. They're just slightly slower, but they're still on the order of 100 years. So what that tells us is that during the last glacial period, you had a recurrence of abrupt climate change with a really large amplitude and going in a few decades to 100 years. But this was not limited to Greenland, and so we can look into other archives. So we've just looked at Greenland ice core, but here was a study looking at marine sediment cores, this time one from the Kariako Basin and one from the Arabian Sea. And here's just looking at luminescence in the marine sediment core. So it's a bit of a complex picture, but here you have the Kariako Basin record, here you have Greenland, and here you have the Arabian Sea. And this we're just zooming in from 30,000 to 48,000 years ago. So sorry, the time is going this way this time. And you don't have to look into all the details, but what's striking here is, again, the fact that you can see those events, this millennial scale variability. You can see it in the Kariako Basin, you can see it in Greenland, you can see it in the Arabian Sea. So when you have a significant warming here, for example, in Greenland, you go from a very cold state to a warm state. You also see in the Kariako Basin, you go from very dry condition to wet condition, and similarly in the Arabian Sea, you go from dry to wet. So not only there were changes in temperature in Greenland, but you can see that the tropical, this is also imprinted in tropical hydrology. So there were changes in the intertropical convergence zone, changes in monsoon. So those are global changes, if you wish. And they're also very rapid. So they're rapid in Greenland, and they're rapid here in the tropics as well. And those events were also seen in Antarctica. So this time we still have a Greenland record. I'm sorry, this time is going there. And we're comparing that with the record of temperature or temperature estimate from Antarctica. And you can see that even in Antarctica, you have an indication of changes happening. The changes are different. The changes are not as abrupt, and they're in antiphase. So when Greenland gets cold, Antarctica gets warm, and then Antarctica cools again, and Greenland warms significantly. So those are global scale events. Those large millennial scale variabilities that you can see in Greenland and high northern latitude. You can see it in the tropics, in hydrology, and you can see it in Antarctica. So what happened? What drove this event? One clue was discovered quite a long time ago, in the late 80s, in marine sediment cores from the North Atlantic. So they recovered marine sediment cores here from the North Atlantic region, analyzed those cores, and when they analyzed them, they found some layers of what they call ice-rafted debris. So those are very coarse grain in what is usually mud in the North Atlantic. So there were layers like that, and those ice-rafted debris, as the name indicates, come from melting of icebergs. So when there is an iceberg getting off or being detached from the ice sheet, it includes in there some lithogenic grain, and when the iceberg goes into here, into the middle of the North Atlantic, it melts, and those grains that are from lithogenic origin are deposited in the sediment of the North Atlantic. So that gives an indication of the dynamics of the event, and it led to the hypothesis that those events were due to changes in the oceanic circulation. So this is a very crude, a very simplified picture of the oceanic circulation today. And as most of you know, one of the main deep water today is the North Atlantic deep water, which is formed in the Labrador Sea and the Norwegian Sea. So the water, as the water moves northward, it gets much colder, it is saline, it is very dense, and can sink to the bottom of the North Atlantic and then flow southward and eventually feed into all the other basins. There's another water mass that we'll talk about later, which is the Antarctic bottom water. But right now, if we focus on the North Atlantic deep water, it has a crucial role for climate in the North Atlantic, but also elsewhere. So the hypothesis is that you are here in the last glacial period, there are ice sheets around, but there is still active formation of North Atlantic deep water in both the Labrador Sea and Norwegian Sea, which drives here the Gulf Stream, so brings a lot of heat northward to the North Atlantic and lead to fairly mild climate. So this is a picture of the Atlantic meridional overturning stream function out of a model. I don't know if all of you are familiar with this, but basically you would have here formation of North Atlantic deep water flowing southward and eventually coming back. And here you have the Antarctic bottom water. And you are here in an interstadial warm phase. And suddenly there is, or gradually, because that's where we are here, there starts to be a decrease in the density at the surface of the North Atlantic, which leads to a weakening of North Atlantic deep water formation. So potentially, let's say you lose your Labrador Sea deep convection site, you still have formation of North Atlantic deep water, but it's weaker. You reduce your meridional heat transport to the North Atlantic, and you start to get colder conditions. And eventually, you go into a very cold event where maybe due to iceberg release or so on, or freshwater input, you decrease significantly the density at the surface of the North Atlantic and stop forming North Atlantic deep water or have very weak formation. In that point, you reduce significantly the meridional heat transport to the North Atlantic, and you can have very cold conditions in most of Greenland and the North Atlantic. So this is the hypothesis. So to test this hypothesis, what we've done is that we've used a model. We've used a coupled model. We brought the model into the condition of the last glacial period, and we add some freshwater input into the North Atlantic to simulate changes in the formation of North Atlantic deep water. So here we have the model in blue and some proxy record in gray. And here we have basically the strength of North Atlantic deep water formation. And here, for example, during this event, we had freshwater to the North Atlantic. We shut down formation of North Atlantic deep water. That leads to very cold conditions in Greenland, in agreement with the Greenland ice core record, and very cold conditions at the surface of the North Atlantic here at the Iberian margin due to the reduced meridional heat transport to the North Atlantic. So basically we can show that by weakening a North Atlantic deep water formation, you have a cooling, air temperature cooling over Greenland and a cooling at the surface of the North Atlantic in agreement with the proxy record, which indicate that maybe all this variability is due to changes in ocean circulation. So you can go you look at other records, and for example, here this is again a very complicated slide, but this was looking at a lake in Turkey, Lake Van, where there is a record over the last 80,000 years, which shows significant changes in hydrology. And all those periods of those dry periods can also be explained by a weakening of North Atlantic deep water formation and colder conditions. So here we have a cold event in Greenland, dry condition in Turkey, weakening of the overturning circulation, cold condition at the Iberian margin, And this is, again, dry condition in Turkey and dry condition in Greece. So we can show that those changes in North Atlantic deep water formation not only have an impact in this region, but they also reach into Europe, into the hydrology of Europe, and they also reach into the Kayako Basin, the Arabian Sea, and here the Ulu Cave in China. Again, all those cold events lead to drier condition in the northern tropics, basically, and the weakening of the monsoon. So this is a bit of the dynamics going on. If we compare what happened to the climate when we shut down the formation of North Atlantic deep water compared to a state where the North Atlantic deep water is active, you can see here the simulated anomaly at the surface of the ocean with weakening of the formation. So here the formation site, deep convection site, was quite north into the Norwegian Sea. As we weaken this formation of North Atlantic deep water, we weaken the meridional heat transport. This leads to a strong cooling all at the surface of the North Atlantic, which extends even to the equator. But so you have a strong reorganization of the meridional heat transport in the Atlantic, and usually the meridional heat transport in the Atlantic is always northward. So here, as you weaken this branch, in fact, you can have increased heat content in the South Atlantic. So not only do you cool the North Atlantic, but you warm the South Atlantic. And this warming can then be spread by the Antarctic circumpolar current to other regions of the Southern Ocean. You can see this into air temperature anomalies as well, with the maximum cooling here corresponding to the change in deep ocean convection and extending over most of the northern hemisphere into the equator. And on the contrary, we have this warming in the South Atlantic, which can extend to most of the Southern Ocean. So all those changes in temperature and temperature gradient have a significant impact on the hydrology, as we said, with all this cooling in the north leading to generally a drier condition because there's a strong reduced evaporation in the North Atlantic, so reduced precipitation in Europe. And we've also increased the temperature gradient in the North Atlantic, so here significantly, which lead to a strengthening of the northeasterly trade winds. And on the contrary here, we've reduced the temperature gradient in the South Atlantic, leading to weakening of the southeasterly trades. And we're shifting the intertropical convergence zone to the south. So there is a drier condition in all of the northern tropics, whereas there is wetter condition in the southern tropics. So really strong hydrological or tropical hydrology response to those changes in North Atlantic. There's also teleconnection to other parts with weakening of the monsoon, which we're not going to talk here in detail. And here I've put a box around most of the North Atlantic because this is what I call the confidence box. This is the box where most of the models will agree and where there are a lot of proxy records to compare with and to try to understand the changes. When we go into Australia, Australasia, or the Pacific, the impact of those events are much less clear for two reasons. A, because there's less proxy records, and also because there are less agreement among models, because there can be other changes happening, other changes, for example, in circulation in the deep North Pacific, etc. And also maybe because most of the models are usually tuned for the North Atlantic. So the Australian region is a much more difficult region to model or to understand. And that's where I guess you all come in, because this is where we, I guess for Australia, we need to understand what's happening. So we definitely need more records on the Australasian or Austral-Pacific region and more modeling work to try to understand the response of those events in Australia, New Zealand, etc. But basically the common ground is this, cooling in the north, warming in the South Atlantic, a bipolar seesaw pattern. So here with cooling here in the north and eventually warming in Antarctica, and the southward shift of the intertropical zone. So this is what I've summarized here for you. But now we're going to look a bit more closely at Antarctica. So again, as we saw, we have here the 7th in Greenland with this cooling and significant warming. And in Antarctica, or if we look here, Heinrich 4, cool condition in Greenland and significant warming at the end with a recovery of the AMOC. And in Antarctica, we have a significant warming of about 2 degrees during the 7th. This is also highlighted here, the same plot I showed you earlier with Greenland on the top, but this time they also stacked up all the Antarctic record, and you can see the difference in shape and in timing in Antarctica. But the problem with Antarctica is that we are not, let's say, there is this hypothesis of simple change in heat transport in the North Atlantic, which can explain the warming in Antarctica. But when you run a multi-model comparison, that means that you do what we call water housing experiment. You just had fresh water in the North Atlantic and look at what happened to the climate in different climate models. So this is the result in different models. You can see that not all the models are going to show a warming in Antarctica. And even if they do show warming, the amplitude of that warming is going to be much less than what the proxy suggest. So maybe the simple view of heat redistribution in the North Atlantic due to change in North Atlantic deep water formation is lacking one mechanism. And one possibility are obviously changes in the south, because now we've all only talked about change in North Atlantic deep water, so changes in the North Atlantic driving all those global changes. But we haven't looked at the possible teleconnection in between the North Atlantic and the Southern Ocean. So one that I won't be talking about today, but it's an ongoing research and very important part of the research is trying to understand how those changes in North Atlantic deep water formation and temperature can impact the southern hemispheric westerlies, which have a significant impact in the Southern Ocean, on the ocean circulation, etc. But there's also the formation of Antarctic bottom water. So here, on the Antarctic continental shelf, there's formation of Antarctic bottom water, so mostly in the Weddell Sea and the Ross Sea. And this formation can also impact significantly the climate or the temperature at high southern latitude. So for example, we've showed here that if you strengthen the formation of Antarctic bottom water, then you can increase your meridional heat transport toward the high southern latitude, and you can have a further warming of the Southern Ocean and of Antarctica. So basically, and I'm going to skip on those. So basically what we've showed is that not only do you have change in North Atlantic deep water, which lead to climate change in the North Atlantic region and the tropics, but you could also have atmospheric or oceanic teleconnection in between the North Atlantic and the Southern Ocean, impacting the Southern Ocean. So the Southern Ocean would not be just a passive responder to the North Atlantic changes, but there could be also obviously active changes in the North Atlantic, triggering or leading to eventually a positive feedback in the southern hemisphere. So this is particularly important for the southern hemisphere, for high to mid-southern latitude, and that's why it's important to understand what are the atmospheric and oceanic teleconnection linking the North Atlantic and the Southern Ocean. And this is also particularly important for the carbon cycle. So this is the last bit of it. Those are changes in atmospheric CO2 as recorded in Antarctic ice core during the 7th. So here again we have Greenland, with, for example, the cold event and the significant warming. Antarctica, warming during this time period, and atmospheric CO2, which indicate an increase of about 20 ppm during those cold events. So all those cold events were associated with change in atmospheric CO2. So maybe 20 ppm doesn't sound much to you right now, but in the natural world, 20 ppm is quite significant. It's about 1/4 of a full glacial interglacial change. And that indicates significant change to the global carbon cycle and potentially ecosystem as well. And what we've showed is that in fact the south, the formation of Antarctic bottom water could be very important for the changes in the carbon cycle. And this is also something you might see today, where you see the importance of the Southern Ocean in sequestering anthropogenic carbon. So Southern Ocean is a region really important for the global carbon cycle. And here we showed that when you shut down the North Atlantic deep water, so this is a view of dissolved inorganic carbon in the ocean, in the Atlantic and in the Pacific. So if you shut down your formation of North Atlantic deep water here, you're going to increase your carbon content in most of the Atlantic Ocean. Okay, and here in the Pacific we have changes. We have reduced carbon content because there is formation of North Pacific intermediate water, which I won't go into today. But we've showed that if you strengthen the formation of Antarctic bottom waters, then you can also ventilate here all the deep part of the ocean, the deep Atlantic and the deep Pacific, and also the Southern Ocean. And you can have an outgassing of carbon through the Southern Ocean. Okay, so what comes out of this is that we have potential changes in North Atlantic deep water, which lead to changes in climate in the North Atlantic and in the South Atlantic, changes in hydrology in the tropics. But those changes in the North Atlantic can also have an impact at high southern latitude, and this is, again, something that is really ongoing research right now, trying to better understand how the North Atlantic can impact the southern latitude, and most likely it is through what we call a tropical bridge, meaning this shift in the ITCZ might be a key to changing the winds or the buoyancy forcing in the high southern latitude. And those changes at high southern latitude can then impact the carbon cycle significantly, leading to, in this case, an atmospheric CO2 increase. And change in atmospheric CO2 increase obviously fit back onto the climate, particularly at high southern latitude. So if you start to increase CO2, then you have warmer conditions over Antarctica and over the Southern Ocean. So this is kind of a positive feedback. Okay. So I'll skip this one, but I'll just say why are we interested in this? You're going to tell me this was just during the last glacial period, which is very different. There was a large ice sheet over the North America. Why would it be relevant today? And one reason is because even though there is much less evidence, it looks like there were significant change in North Atlantic deep water even during warm period. So here, for example, this is the last interglacial period, about 125,000 years ago, where this is a record by Gallas and et al. In the North Atlantic. And what's the evidence? The evidence, significant weakening of North Atlantic deep water formation during this warm period, 125,000 years ago. So showing that this can also happen in a warm climate, even though it's less frequent. And I guess the most important piece of evidence is also the future projection in North Atlantic deep water. So those are results of models. So those are CMIP5 model forced under the RCP 8.5 until 2100. And you can see that, so I haven't put the name of the model, but those are all the models I looked into. All of them show a significant weakening of North Atlantic deep water. Sorry, it's not going to 2100. Here it's going to 23, and here it's going to 21. They all show a significant weakening of North Atlantic deep water. Here this is put in percent, with somewhere in between 15 and 60% change in North Atlantic deep water formation. And this is not taking into account any changes in ice sheet. So this is a simple change in climate impact. So if you assume or suspect that there will be changes in Greenland mass balance, so this could impact even further North Atlantic deepwater formation. So this is not completely science fiction, and this is why it's important for us to try to understand all those teleconnections and all the changes that happen under a weakened North Atlantic deepwater formation. And those are just my conclusion. So past records indicate a period of abrupt climate change. Climate can change in less than 100 years, and this was driven by changes in what we call the ocean circulation, particularly North Atlantic deep water. And we know it had a global climate impact, so with impact as far as Asia and Antarctica, and also a global carbon cycle impact. And we should be concerned, or we should, it's important, let's say, to understand those events because there is evidence of such events during past warm period, and there is an indication that the North Atlantic deep water might decrease during the 21st century and beyond. And it is even more concerning taking into account the fact that the Greenland and Antarctic ice sheet in those CMIP 5 scenarios were not taken into account. So obviously if Greenland lose mass, it will weaken North Atlantic deepwater formation. And that's all. Thank you. Question maybe, or no question? Yes?
I think you tried to explain it a bit, but on the temperature, when you talk about variability, there was a gradual decline in the temperature and then a very rapid increase.
Yeah.
And you tried to explain that with one of the early plots with the ocean circulation, and I didn't quite understand.
Well,
So rapid?
basically what we think is so rapid is because it's a recovery of North. So let's go back to, I can go faster. Oh, sorry, it's reversed on that. I'll never manage. Okay, here. So, yes. So, for example, for this one particularly, you see it's very, very gradual. And here, this one is not really an Heinrich event, but maybe this one is an Heinrich event. So, the hypothesis is that there's a gradual decline in North Atlantic deep water, but this is still something that we're really trying to understand because there's no direct proxy for changes in the overturning or changes in the water mass formation. So there are some that we can use, but they're not direct. And we can use models, but it's very rare that a model will go so slowly in decreasing North Atlantic deep water. Obviously, it depends on the forcing, but yeah. And then here you would have a significant weakening of the North Atlantic deep water. But what is, and you're right here, is that the overturning recovers extremely quickly. And actually most models will do that. If you had a bit of fresh water, you would shut it down and you let it sit. And here actually you see it. It's not that rapid. The first phase, there's a small initiation of deep convection, and suddenly it just recover. Because you start to bring more saline water to the North Atlantic, you start to have slightly warmer conditions. I mean, this is all feedback in between circulation, sea ice, and deep ocean convection. But yeah, that would be just a very fast recovery. But right now we are more into going into the slow weakening phase, if anything, because the overturning, well, yes, I know, the overturning is very strong, even though there is indication that it has weakened over the last century. So there has been an increased literature over the last, like just some papers came out last month, but one in 2015 showing that the overturning had weakened over the beginning of the 20th century, and we are going technically towards a slow weakening, not a shutdown, but more a slow weakening. Yeah. No more question? Okay. Thank you.